Welcome back. So in this video, we're going to have a look at three photos. I'm going to do a little bit of circle geometry and some trigonometry and see if we can't make some predictions. So the first predictions that we'll make will be based on the Earth being flat, and we'll then make some predictions on the Earth being a globe. So the first photo we're going to look at is from Beyond Horizons, and this photo was made fairly famous in a video by Taboo Conspiracy. And he's basically caused a lot of flurfers to make absolute fools out of themselves over these online curve calculators like Metabunk. The observation is from Grignetta in Italy, across to two mountains. Mont Blanc is on the left, and Grand Tourmaline on the right. As you can see from the photo, Grand Tourmaline appears very slightly higher than Mont Blanc. So let's have a look at what a flat Earth model would predict and compare that to what a globe model would predict. Okay, so we've got Grignetta on the left here, and its elevation is 2,177 meters. Grand Tourmaline is 132 kilometers away, and Mont Blanc is 196 kilometers away. So first of all, we've got our eye level. That just goes straight across, parallel with the ground on a flat Earth. Then we have our line of sight between Grignetta and the top of Grand Tourmaline. And Grand Tourmaline is 3,379 meters high, but our observer is already 2,177 meters high, so we're looking up a further 1,202 meters. Our line of sight to Mont Blanc, and Mont Blanc is 4,810 meters high. So from our observer at 2,177, we're looking up a further 2,633 meters. So with those figures that we have 1,202 meters over a distance of 132 kilometers and 2,633 meters over this distance. We can do some pretty simple trigonometry using the tangent formula and work out our viewing angle or angle of elevation, and that's basically an arctangent formula. So on a flat Earth, the angle to Grand Tourmaline is 0.52 degrees, and the angle to Mont Blanc is 0.77 degrees. So on a flat Earth, Mont Blanc should appear higher in your perspective view on a flat Earth. Okay, so now let's have a look at the globe maths. So for that, it gets a little bit more complicated, but the way I like to visualize it is with a circle that represents the Earth, and the center of that circle is centered around the origin at 0, 0. So we take the accepted value for the radius of the Earth, which is 6,371 kilometers, and we stick our observer up on the top of the Grignetta Peak, which is a further 2 kilometers and 177 meters higher. So the coordinates on the Cartesian plane for our observer are x equals 0 and y the radius plus the height. Okay, now we need to draw a line from the radius to represent our peak at Grand Tourmaline, and we need to find out the Cartesian coordinates of our tippy top of that peak. So the first thing we do is try to find this angle in here. Now we know that the distance between Grignetta and Grand Tourmaline is 132 kilometers, and we know that the radius of the Earth of 6,371 will give a circumference of about 40,000 kilometers. So all we need to do is take the proportion of 132 kilometers over 40,000 kilometers to give us this degree in here. So the angle between the two points to our observer and the tip of the peak is 1.19 degrees. We also know that Grand Tourmaline is 3,379 meters above sea level, which is 6,371 plus that height, and that is basically the hypotenuse of a triangle. So to get the XY coordinates for this point, we do some fairly simple trig. Get our x value with that, the sine function, and the y value with the cosine function. And they are our x and y coordinates for that point. So now we can draw a straight line between our observer and the top of Grand Tourmaline. And this is our line of sight, which is now a right angled triangle. And that's what we are trying to get. So basically we're looking 132.06 kilometers this way and 166 meters down. And I've obviously written a spreadsheet to do all this rather than doing it manually all the time. You basically input your observer height here. The mountain in the foreground is Grand Tourmaline and its distance from you. On a flat Earth, the distance between your observer height and the height of the mountain, as we saw in the first slide, was 1,202 meters, and we came out with a viewing angle or an elevation angle of 0.52. On the globe, we worked out that the angle of rotation over 132 kilometers was 1.19 degrees, and we worked out our x and y coordinates. And then we had our little triangle, which was 166 meters high by about 132 kilometers long. And that gives us a viewing angle of negative 0.7 degrees. So almost horizontal, but looking very slightly down. With the second peak, Mont Blanc, its height is 4,810 and it is 196 kilometers away. So we do the similar calculations to work out our viewing angle on a flat plane of 0.77 degrees, and then we see what our viewing angle is on the globe, which is minus 0.11 degrees. Now, this is where the predictions come into it. On a flat plane, Mont Blanc should appear higher than Grand Tourmaline. On a globe, however, Mont Blanc should appear lower than Grand Tourmaline. So let's go back to our image and see what happens. And as you can see, Grand Tourmaline is higher and Mont Blanc is lower, and that fits with the globe prediction and contradicts the flat Earth prediction. So it's globe 1, flat Earth 0. Alright, so let's look at another Beyond Horizons video, or photo, sorry. This one is from Pic de Fenestrellet, looking at Grand Ferrand, which is this one here, and Pic Gaspard, which is this one here. It's actually the world record holder for long distance photography from Earth. So again, I've written that spreadsheet to basically do the math for me, sticking in the height of the observer at Fenestrellet of 2,820, and then the height and distances to the two mountains. On a flat Earth, looking at Grand Ferrand should be very, very close to horizontal, and Pic Gaspard should be higher. So the flat Earth prediction is that Pic Gaspard should appear higher. The globe prediction is that Grand Ferrand should appear higher and Pic Gaspard should appear lower. So let's see what the picture says. As you can see quite clearly, Grand Ferrand is the highest mountain in this photo, and Pic Gaspard is quite low. So that makes it globe 2, flat Earth 0. Alright, so our last one is looking at Isle of Man from the hill at St. Bees. The mountain on the left is actually the tallest on the Isle of Man, Snaefell, at 621 meters, and it's 61.2 kilometers away. The mountain on the right is North Barul, 561 meters and 56 kilometers away. So again, let's go to our little spreadsheet. Plug in an observer height, which, there's a lot of debate over the observer height, but it doesn't actually make a whole lot of difference in the end to the numbers. We'll say 35 meters. North Barul, 561 meters and 56 kilometers away. Snaefell, 621 meters high and 61.2 kilometers. On a flat Earth, Snaefell should appear very slightly higher, 0.55 degrees to 0.54 degrees. On a globe, North Barul should appear very slightly higher than Snaefell. And as you can see, North Barul appears higher than Snaefell, very, very slightly though. So that is 3-0 to the globe. Woohoo! Now, what I would like people to do is actually take a theodolite up to any of these peaks and measure the angles to the top of these peaks. Now, it's a little difficult to do at St. Bees looking across to the Isle of Man because the angles are very small, but I believe the theodolite should be able to tell the difference between an angle of, say, 0.28 and an angle of 0.54. With the Pic Gaspard versus Grand Ferrand photo, the angle to these mountains is around 1.8 degrees down, which should be very clear on a theodolite. So, will anyone take up the challenge? And for really, really, really big bonus points, if the angle measurements that you do take with a theodolite don't match exactly to what I've calculated, can you figure out why?